Have you ever stopped to think about how your phone just understands your voice? Or how Spotify streams music that's perfectly clear with no skips right to your headphones? Well, it turns out there's this invisible force, kind of like a hidden engine, that's powering pretty much every piece of tech we use today. And today, we are pulling back the curtain on that engine: digital signal processing.
So, here's what we're going to cover. We'll kick things off by figuring out what a signal even is. Then, we'll get into the whole analog versus digital thing. After that, we're going to uncover the absolute magic of turning waves into numbers, see how we can literally sculpt those numbers with pure math, and finally, we'll see just how deep this unseen engine runs in our everyday lives. All right, first things first, let's get down to the basics. We are living in a world that is just, well, swimming in signals, nonstop all around us. But what does that really mean? At its heart, a signal is just something that carries information. Think about it this way. The music you're listening to, that's the useful signal, the stuff you actually want. But the static you might hear on a bad connection, that's also a signal. It's just unwanted junk that we call noise. And really, the entire game of signal processing is about telling the difference between the two. You could almost say signal processing is the art of taming this wild, chaotic sea of information all around us. It's how we find that tiny needle of useful data in a giant haystack of random noise. And once we find it, we can make it stronger, clearer, and get it ready to be saved or sent anywhere in the world. Okay, so how do we actually do all this processing? Well, we basically have two paths we can take. We can either work with signals in their natural, kind of messy, continuous analog form, or we can translate them into the clean, precise language of computers, the digital brain. On the one hand, you've got analog processing. This uses actual physical hardware, resistors, capacitors, to mess with a continuous wave directly. It works, for sure, but it's pretty rigid, and the signal can get weaker or distorted over time. But digital signal processing, oh, that is a whole different beast. It chops up that continuous wave into a bunch of discrete numbers, and then it uses code to play with those numbers. And the big win here? It's infinitely flexible, and a digital copy is a perfect copy, every single time. This whole digital process works kind of like a four-step dance. First, an analog to digital converter, or an ADC, grabs that real-world signal and translates it into a string of numbers. Then, step 2, the digital processor, which is really the brains of the whole operation, does all the cool stuff to those numbers. Third, a digital to analog converter, or a DAC, turns those processed numbers back into a rough analog signal. And finally, a post filter smooths everything out, giving you that perfect, clean wave you can actually hear or see. But let's back up a second, because that first step, going from the analog world to the digital one, that's where the real magic happens. The whole process is called sampling, and believe me, it solves a huge problem. I mean, really think about that for a second. A sound wave is smooth, it's flowing, it has an infinite number of points along its curve. How in the world can you represent that perfectly with just a limited list of numbers? It sounds totally impossible, right? Well, the answer is sampling. You see, you don't try to capture the entire wave all at once. Nope. Instead, you take these super fast measurements, or samples, at perfectly regular moments in time. It's a lot like a movie camera. A camera doesn't record continuous motion. It captures 24 still pictures every second. Our brains fill in the gaps so we see smooth movement. In a very similar way, DSP can rebuild a perfect wave from all these little digital snapshots. And this brings us to what is basically the golden rule of the digital world, the Nyquist-Shannon sampling theorem. It's this incredible, mind-blowing idea that says, as long as you sample fast enough, specifically more than twice the highest frequency in the signal, you lose absolutely no information. Just like that sink in, you can take a finite set of numbers and perfectly recreate an infinite continuous wave. This one concept is what makes everything from your CDs to your Wi-Fi even possible. Okay, so we've got our wave turned into a stream of numbers. Now the real fun begins, because now we can use pure mathematics to sculpt that data into pretty much anything we want. And to show you how, we're going to use a real audio example from our source material. We're going to take a piece of music I'm pretty sure everyone knows, the Hallelujah Chorus. Using a tool called MATLAB, we can load this audio file up and see it for what it is in the digital world, just a long sequence of numbers all ready for us to play with. So what we're going to do is add an echo, and the source material tells us exactly what to listen for. It says, you should be able to hear the distinct echo of the chorus in about a half second. Let's see the code that actually makes this happen. And just look at how simple this is. With just a couple lines of code, we're setting the echo's strength and its delay. Then we create what's called a filter. And that last line, that's the key. It applies this mathematical filter to our original sound, and poof, it creates a brand new one with the echo baked right in. We have fundamentally changed the signal with nothing more than a little bit of math.
So, that echo is now part of the data. You can't separate it from the music. But what if that was a mistake? What if we wanted to undo it? Can we use this same incredible technology to reverse the process? Can DSP actually remove the very echo that it just created?
And the answer is a huge, resounding yes. The source material confirms it. DSP can be used to effectively reduce and even almost eliminate echoes by designing what's called an inverse filter, basically a math operation that does the exact opposite of our first one. We can process the signal again and just cancel out that echo. It's a perfect example of the incredible power and precision of digital processing.
Now, adding and removing echoes from a song, that's just one tiny application. This core idea, turning signals into numbers and using math to filter them, it's truly the unseen engine that makes our modern world go round. I mean, just think about how far its reach extends. For speech and audio, it's the magic behind your noise-canceling headphones and the voice recognition on your phone. For images and video, it's what compresses movies so you can stream them on Netflix and sharpens the photos you take. It's absolutely critical for military radar, for guiding missiles, and even for cleaning up those amazing images from the Hubble Space Telescope. And yeah, of course, our entire global communications network, cell phones, Wi-Fi, digital TV, it all runs on DSP. So in the end, it's this silent mathematical force that decodes, enhances, and transmits the data that defines our modern lives, which leaves us with one last, really fascinating question to think about. As our signals get more and more complex and packed with more and more data, what new worlds will digital signal processing allow us to see and hear next?